Welcome to this explainer. Today, we're treating the EPA's Performance Specification 5 like the ultimate rulebook for a pretty high-stakes game of environmental compliance. If you've ever wondered exactly how industrial facilities are legally forced to prove they aren't just pumping dangerous sulfur compounds into the air, you are absolutely in the right place. We're going to take this dense, highly technical regulatory document from October 2020 and break the whole thing down. We're decoding the strict parameters that separate a passing grade from a massive environmental violation. So let's just dive right into it. Okay, before we get into the really heavy rules, let's establish the key players on the board here. Our main target? That's Total Reduced Sulfur, or TRS. This is our highly hazardous analyte, literally the specific substance we're hunting for. And to catch it, facilities use what's called Continuous Emission Monitoring Systems, usually just abbreviated as CEMS. Think of CEMS as these sophisticated, round-the-clock technological watchdogs that are installed straight into industrial smokestacks. Performance Specification 5 is the exact test used to evaluate whether or not these monitors are actually doing their job correctly, either when they're first installed or whenever the regulations demand a checkup. Now, to navigate all this dense text efficiently, we've structured this explainer into 4 critical levels: the scope of Specification 5, critical safety precautions, sampling strategies and methods, and finally, measuring performance. Section 1, Scope of Specification 5. Let's look at exactly when this applies and the foundational rules it builds on. What's really fascinating here is how the EPA structures these regulations. You see, Performance Specification 5 doesn't actually reinvent the wheel. Instead, it relies heavily on a parent rulebook known as Performance Specification 2, or PS2. According to Section 1.3 of our source document, PS-5 just directly borrows its core definitions, equipment setups, and baseline test procedures, like those for determining calibration drift and relative accuracy, right out of PS2. So to really understand these TRS monitoring rules, an engineer absolutely has to be deeply familiar with that foundational text as well. Section 2, Critical Safety Precautions. Let's immediately establish the real-world stakes here. Because the EPA document does not sugarcoat the hazards. Right there in Section 5.0, they explicitly warn that this process involves actively dangerous materials. I mean, when technicians are testing these monitors, they're dealing directly with highly toxic total reduced sulfur gases, not to mention complex, high-voltage industrial equipment. The regulation makes it crystal clear. Simply following this performance specification does not automatically keep you safe. It's just a guide for the equipment, right? Not a comprehensive safety manual for the human beings actually doing the work. Because of that, the ultimate responsibility falls squarely on the user. The document mandates that it is entirely up to the facility and the technicians to consult the specific CEMS manual and establish rigorous health and safety practices before ever stepping onto the playing field. They literally have to figure out all the applicable regulatory safety limitations before they even attempt these analytical procedures. Section 3, Sampling Strategies and Methods. With safety locked down, let's check out the actual plays for gathering a valid sample. So depending on the applicable subpart of the regulations, a facility is going to use Method 16, 16A, or 16B. Method 16 requires a sample made up of at least 3 separate injects, equally spaced out over time. Now, if you go with Method 16A, your sample has to be continuously collected for at least 1 full hour. And then for Method 16B, you have to analyze a minimum of 3 distinct aliquots, which, by the way, are just small, equal-sized sample portions, spaced evenly over the duration of your test period. But here is the crucial point to remember for any of these methods. According to Section 11.0, your sample collection and your analysis absolutely must happen concurrently. You can't just bag a sample, throw it in the back of a pickup truck, and test it a week later. The whole nature of continuous emission systems means the reference sampling and the analysis are happening at the exact same time. This ensures you're getting a true, real-time comparison against what the CEMS is reporting. Okay, so we've got the sample, and we've got the monitors running. But what is the actual threshold for success? Well, before we reveal the incredibly strict math required to pass this test, take a quick second to hit that subscribe button. It really helps us keep bringing you clear, structured explainers just like this one. Section 4, Measuring Performance. Let's find out the exact score required to win this compliance game. The first major hurdle here is calibration drift. Basically, the CEMS detector calibration simply cannot drift or deviate from the reference value of the calibration gas by more than a strict 5% of the established span value. This is testing whether the machine can hold a steady baseline reading without its sensors wandering off target over time. To really put that 5% into perspective, let's look at an example. For subpart BB sources, where the span value is 30 parts per million, that 5% margin equates to a tiny 1.5 ppm allowable drift. I mean, we are talking about microscopic levels of gas here. If that monitor wanders off by just 2 parts per million, boom, it fails the test. And it gets tougher, because this is an endurance test. You have to maintain this incredibly tight 5% calibration tolerance for 6 out of 7 test days. It's definitely not enough to just be accurate for a few hours. Plus, if the CEMS happens to include both pollutant monitors and diluent monitors, like oxygen monitors, for example, the calibration drift has to be calculated and pass separately for each individual component. Now, beyond calibration drift, we also have to look at relative accuracy. This compares the monitor's actual readings against that trusted reference method we talked about earlier. The rule here is that the relative accuracy of the CEMS must be no greater than 20% off when your calculation is based on the average reference method value. Alternatively, that allowable margin of error can shrink significantly. The relative accuracy must be no greater than 10% if the calculation is based directly on the applicable emission standard itself, rather than that average reference method value. So it really demands a highly precise alignment between what the machine claims is coming out of the stack and what the reference test proves is actually there. When you look at them side by side, you can really see how Performance Specification 5 totally boxes the monitor in with these strict, uncompromising parameters. It demands daily precision through that 5% calibration drift rule, and then overall accuracy through the 10 to 20% relative accuracy rules. This dual-layered approach ensures the monitor isn't just accurate on average, but is consistently reliable, day after day. So as you review these demanding regulations, I want you to consider this. Are these rigid equations and percentages the true safeguard keeping our air clean? And what happens the exact moment a monitor drifts just a fraction of a percent too far, crossing that 1.5 part per million threshold? The rules are clearly defined, sure, but the ongoing execution of these rules is what truly protects our environment. Thanks so much for joining me for this explainer, and as always, keep questioning the data.